You know, in just about any factory or power plant, really any automated system, there's this unsung hero chugging away in the background. It's called a programmable logic controller, or PLC for short. So today, we're going to crack open this rugged little digital brain and see exactly what makes it tick.
All right, here's our game plan. We're going to start with the PLC's core, its brain. Then we'll map out its memory, see how it listens to the world through its inputs, and then how it gives orders with its outputs. And we'll wrap up with the most fundamental sensor of all, the switch. So let's jump right in with the digital brain itself. So at its heart, a PLC is really just a specialized computer. But here's the thing. It's not sitting in a nice, clean, air-conditioned office. Nope. Its home is the factory floor, noisy, dirty, and super demanding. These things are built tough, designed to run nonstop, 24/7, without a single complaint. Okay, take a look at this diagram. It gives you the whole picture. Over on the left, you have signals coming in from the real world. These are the imports. They travel along that central highway, the data bus, right to the processing core. That's where the brain makes all its decisions. And once it decides what to do, it sends commands back along that same bus to the output terminals, which then control things like motors, lights, and valves.
You know, it's a lot like the processor in your laptop or phone. The PLC's microprocessor is constantly grabbing and carrying out instructions from its memory. But unlike a regular PC that's juggling web browsers, music, and a dozen other things, a PLC is laser-focused on just one thing: industrial control. And that specialization is what makes it so incredibly fast and reliable at its job.
And that job? Well, it all boils down to the simple, relentless loop. First, it scans all the inputs to get a snapshot of what's happening right now. Step 2, it takes that information and runs it through the program, the logic that an engineer wrote. And finally, Step 3, it updates all the outputs based on what the program decided. Then, it does it all over again, thousands of times a second. It never stops.
But for that processor to know what to do, it needs its instructions, right? And those instructions have to live somewhere. That somewhere is its memory. So let's take a little tour of the PLC's memory map. So, a PLC usually has 3 key neighborhoods in its memory. First up is the system memory. You can think of this like a PC's BIOS. It's the permanent operating system that the manufacturer puts in. Then you have the program memory. This is where the custom logic, the actual instructions you or an engineer writes, gets stored. And last, there's data memory, which is basically a temporary scratch pad the PLC uses to jot down values while it's running the program. This visual is a fantastic way to picture how a PLC reads its program. Think of that address counter like your finger pointing to a line in a recipe book. It points to the first instruction, the PLC reads it and does it, and then the finger moves to the very next line, and so on, stepping through the entire program, one instruction at a time.
And this little two-step dance has a name, the instruction and execution cycle. The instruction cycle is the fetch part, where the PLC goes and gets the command from memory. The execution cycle is the do part, where it, actually does the thing. This simple loop, fetch, do, is the very heartbeat of every single PLC out there.
Okay, so we know how the PLC thinks, but how does it sense the world around it? How does it know if a button has been pushed or a sensor has been tripped? Well, that's the job of the input section. This is where physical reality gets translated into ones and zeros.
So the input module has 2 absolutely crucial jobs: conversion and protection. It takes a higher voltage signal from a sensor, like say 24 volts, and safely steps it down to the 5 volts that the delicate little microprocessor can actually handle. It also has to protect that processor from dangerous power surges. It often does this with something called an optocoupler, which is super cool. It actually uses a beam of light to send the signal across a physical air gap, creating a bulletproof barrier. Now, when it comes to wiring inputs, you've got 2 main flavors: syncing and sourcing. And it really just comes down to which way the electricity is flowing. Here's a simple way to think about it. A syncing input is like a drain. It accepts current flowing from the sensor. A sourcing input, on the other hand, is like a faucet. It provides the current that flows out to the sensor. And you can see exactly what I mean in these diagrams. On the left, with the syncing input, you can see the current flows into the PLC terminal. But on the right, with the sourcing input, the current is flowing out of the PLC. The most important thing here is that the PLC and the sensor have to be a matched set, either sync to source or source to sync, for the whole thing to work. All right, so the PLC has received the signals, it's crunched the numbers, and it's run the logic. Now what? Now it's time to act. Let's check out the output section.
This is how the PLC flexes its muscles and actually controls devices out in the real world. Generally, we see two main types of outputs. First, you've got transistor outputs. These are solid state, which means no moving parts. They are super fast and last practically forever, but they're really only for switching low-power DC stuff, like little indicator lights. For the heavy lifting, you need relay outputs. These are actual physical electromechanical switches that can handle big AC or DC loads. We're talking about things like starting a massive motor. And here you can see them side by side. See the symbols on the left that look like little physical switches? Those are the relays controlling the big, heavy loads. Then on the right, you have the transistor symbols switching the smaller stuff like lights. It's really all about using the right tool for the right job.
Now that we've covered how a PLC gets information and how it acts on it, let's zoom way in. Let's talk about the most fundamental input device there is, the humble switch. It is the simplest possible way to tell a PLC if something is on or off, open or closed, here or there.
At the end of the day, a switch does one incredibly simple thing. It makes or breaks an electrical circuit. When it's open, there's a physical gap and electricity can't flow. The circuit is off. When you flip it and it's closed, the contacts touch, the circuit is complete and current can flow. For a PLC, this is the most basic piece of information imaginable. A 1 or a 0, on or off.
To describe all the different kinds of switches out there, we use two key terms, poles and throws. It sounds a little technical, but it's pretty straightforward. A pole is basically the number of separate internal switches that get moved by a single lever or button, and the throw is the number of on positions that each of those internal switches has.
This table shows how it all fits together. A single pole, single throw, or SPST, that's just your basic on-off light switch. But when you start adding more poles or throws, you can do more complex things. For instance, a double pole switch is like having two totally separate switches controlled by one lever. That means you can control two completely different circuits at the exact same time. And this really brings us back to the big picture. Getting a handle on this fundamental hardware, from how the processor runs its scan cycle all the way down to the simple mechanics of a switch, is the bedrock of industrial automation. You have to know this stuff to build systems, to fix them when they break, and, most importantly, to secure them from attack.
And that leaves us with a pretty critical question, doesn't it? We've seen that a PLC is an amazing follower. It will execute its logic perfectly, thousands of times a second, without question. But what happens if it's acting on bad information? What if an attacker can lie to its sensors, feeding it a completely false version of reality?